Hello, I'm Donna Erickson, and I'm working with Ting Huang and Caroline Menezes about temporal organization of spoken utterances from an articulatory point of view. Our approach is that speech is organized articulatorily to produce a series of syllable-sized units as the speaker opens and closes the mouth. These are jaw tracings, showing jaw opening and closing patterns for 3 different sentences in 3 different languages. These figures are from work done by Vattikiotis Bateson and Kelso. The top image shows the jaw tracings of a Japanese speaker producing a sentence with 21 syllables and 21 jaw openings. Oba-san wa momo o hirote ie ni motte kairimashita. The next one is a French sentence. La férocité naturelle fait moins de cruel que l'amour propre. 17 syllables and 17 jaw openings. The bottom one is an English sentence, again 17 syllables and 17 jaw openings. There is, according to legend, a boiling pot of gold at one end. Thus, spoken utterances are a series of mouth openings and closing. Each opening closing is a syllable unit. Maximum opening of the jaw is referred to as vowel. Maximum closings, onsets and offsets, is consonants. How much the jaw opens during each syllable is determined by the characteristics of the vowel phoneme. High vowels have less jaw opening than low vowels. But look at the biggest jaw opening in the English sentence. It is for the vowel I in is. This vowel is stressed in the sentence, and it is at the end of a phrase. So we see that stress and phrase boundaries affect how much the jaw opens. For many languages, such as Japanese and French, the jaw opens more at the end of the utterance. But for English, we don't necessarily see that. Here are jaw tracings for the phrase, I saw 5 bright highlights in the sky tonight. The vowel is the same for each of the content words, but the amount of jaw displacement changes. The largest jaw opening is on sky, and then on 5. The amount of jaw opening changes relative to other syllables within the grouping units. The key word in each grouping unit, intermediate phrase, intonational phrase, gets the most jaw opening. In this way, the amount of jaw opening can be seen to mark the hierarchical relationships among the syllables within a group. That is, within each grouping unit, one syllable will have more jaw opening than the others. A speaker marks which syllable in a grouping unit is most important by opening the jaw more. The take-home point. Each syllable in a given utterance has a measurable amount of magnitude, based on the maximum jaw displacement at the nucleus of the syllable, and determined by its position in the prosodic structure of that utterance. What are the acoustic consequences of increased jaw displacement? Well, formants. Depending on the vowel characteristics, the first and second formant vary with increased jaw displacement as the tongue moves to preserve the phonemic identity of the vowel. For contrastive emphasis, F1 was found to increase with increased jaw displacement regardless of vowel height. Other acoustic changes are intensity, duration, and F0, which also may occur with increased jaw displacement, but not necessarily. Well, what about nuclear stress? Nuclear stress often occurs on the rightmost content noun of the utterance. Nuclear stress can be elusive to non-first language speakers of English, and frequently even to first language speakers. Sometimes it's not necessarily clear which of the items in the utterance has nuclear stress, perhaps because prominence is not phonologically specified. A speaker could produce several tokens of the same utterance with nuclear stress on a different content word. For instance, I saw 5 bright highlights in the sky tonight. It could be on sky, or highlights, or 5. Given that nuclear stress is elusive, how do we know where it is? One approach to answering this question is the one proposed by Cole et al., rapid prosodic transcription. In this method, naive listeners are asked to specify which syllable or word in an utterance receives prominence. The more times a word syllable is marked as being prominent by listeners is interpreted as representing the amount of perceived prominence in that word. This pilot study then asks, what are the most prominent words for the perception of nuclear stress, and does the jaw open largest for nuclear stress? We looked at the sentence, I gave dates to Kay today, spoken by 2 American English speakers, and 5 randomizations of sentences from a computer display. The acoustic and articulatory data were recorded at Japan Advanced Institute of Technology, and we focused on the jaw and the tongue blade. So here is a display of the acoustic and articulatory data. The top panel is audio, then spectrogram, and then the articulatory data, tongue, blade, and jaw. The measurements are made at the maximum jaw displacements from the occlusal plane for the E part of the A diphthongs for the 4 words gave, dates, K, and day, as shown by the red vertical lines. The first word of the sentence, I, as well as the reduced syllables for 2, are not measured since the vowels are different. About the perception tests, they were presented by computer over headphones and 19 listeners. The instructions were mark with a line underneath the word if some words stood out more than others, they were louder, longer, or higher pitched. And the number of times a given word is underlined determines its level of perceived prominence. Now here are the results, the jaw and prominence ratings. This figure shows the patterns of jaw displacement and prominence ratings for each of the tokens of the sentence for each of the speakers. 4 tokens for A9 on the left and 5 tokens for A10 on the right. The x-axis indicates each content word in the utterance, gave, dates, K, and day. Red dotted lines referred to the standardized jaw opening values, and green solid lines indicate perceived prominence, with the green band representing standard deviation of perceived scores. Normalized values of jaw displacement in millimeters are in z-scores by token for each speaker. Correlation analyses show a significant correlation with jaw and prominence for both speakers. Notice that for all tokens, maximum jaw displacement occurs on the word K, peak in the red dotted line. This is the word that generally sees a peak in the solid green line perceived by listeners to be the most prominent. These results suggest that indeed speakers open the mouth more to indicate a word in the sentence which is both intended by the speaker as well as perceived by the listeners to have nuclear stress. Our findings are that increased jaw displacement for changes the acoustic information which listeners can use to recognize nuclear stress in English. But what are these acoustic changes? Significant relations related to F0 informants and jaw were also found between F1 and tongue blade minus jaw, F2 minus F1 and tongue blade minus jaw, and F1 minus F0 and tongue blade minus jaw. Specifically, between F1 minus F0 and tongue blade minus jaw, especially for speaker 10. Thus, for the mid-front vowel, we see an interaction among jaw, tongue body, F1, F2, and F0. Because of the limited time, we are not discussing the F0 patterns, but these are discussed in the paper version. Articulation of nuclear stress for mid-vowel E. We found increased jaw displacement for mid-vowels, but we note that for nuclear stress on the low vowels A and A, the correlation between jaw and perceived prominence appears to be more robust than that found for the mid-vowel. This was reported in earlier studies. But for the mid-vowel E, we find a linking between the jaw and the tongue, such that increased jaw displacement shows significant correlations for tongue blade minus jaw with F1, tongue blade minus jaw with F2 minus F1, and tongue blade minus jaw with F1 minus F0. Given that increased prominence on the mid-front vowel requires the tongue blade to move more forward to compensate for the increased jaw lowering, it makes sense to see significant correlations with tongue blade minus jaw and the formants. Also, Given the interaction between tongue, jaw, and larynx, it makes sense to see significant correlations with F1 minus F0. An interesting application of this type of approach to temporal organization of spoken utterances is with second language teaching of prosody. The top panel shows jaw patterns for an English speaker, and these are different from those of a Japanese speaker, bottom panel. Notice that compared to the English speaker, the Japanese learner of English opens the jaw more at the end and at the beginning, as would be done if he were speaking Japanese. Thus, teaching articulatory rhythm may be an effective way to teach a second language and would be different than teaching the acoustic rhythm pattern done generally through the reiterative speech. And this topic is discussed by a paper given at the same meeting by Wilson et al. Another application of our findings is about the understanding of the temporal organization of speech. Since this is a special session on temporal organization of speech, we would like to take a moment to talk about a model of temporal organization that captures important aspects of how spoken language is organized. This model needs a great deal of development before it can actually be tested, but we think it's quite interesting and holds great promise. In this approach to temporal organization, we equate amount of jaw opening with syllable magnitude, as proposed by Fujimura. There are 4 parts of the model, ranging from the prosodic input, metrical tree, at the top, to the actual movements of each of the articulators at the bottom. This is called articulators. The second to the top, converter, shows how the metrical grid is translated into syllable pulses and boundary pulses, and the next, distributor, shows how the information in the converter turns into consonants and vowels. And the final image shows which particular articulators are used to produce the segments. Notice that the prosodic component affects the implementation of the consonants and vowels. The research that we are doing focuses on the top 2 sections, the metrical grid and the converter, which converts the metrical grid information into a series of syllable pulses and boundary pulses. Here is a metrical tree for the sentence, "That's wonderful," which then outputs the prominence of each syllable, syllable 1, syllable 2, syllable 3, and syllable 4, in terms of syllable pulses of varying sizes, which is essentially equivalent to the amount of jaw opening for each syllable. It also outputs boundary pulses at the beginning and the end, and after that's. How to determine boundary pulses from jaw displacement is described in our ICPH 2015 paper, referenced in the written version of this paper. Conclusion. Our main finding is that more jaw opening, more perceived prominence. We believe this work is an important addition to elucidate temporal structures of speech from a syllable point of view, as well as applications to teaching spoken language rhythm to second language learners. Future work requires more utterance types, more speakers, more listeners, more acoustic analyses related to changes in both source and filter, and more application of articulatory findings to the development of a model of temporal organization of speech, specifically the CD model. We thank you for listening. We look forward to hearing questions and comments sent to our emails or my Skype name. Thank you very much.